Projective Geometry, Volume 1, by Oswald Veblen and John Wesley Young.
Chapter 4, Harmonic Constructions and the Fundamental Theorem of Projective Geometry, Section 40, Types of Collineations in the Plane. We have seen in the proof of Theorem 10, Chapter 3, that if O1, O2, O3 is any triangle, there exists a collineation pi leaving O1, O2, and O3 invariant, and transforming any point not on a side of the triangle into any other such point. By Theorem 18, there is only one such collineation, pi. By the same theorem, it is clear that pi is fully determined by the projectivity it determines on two of the sides of the invariant triangle, say O2, O3, and O1, O3. Hence, if H1 is a homology with center O1 and axis O2, O3, which determines the same projectivity as pi on the line O1, O3, and if H2 is a homology with center O2 and axis O1, O3, which determines the same projectivity as pi on the line O2, O3, then it is evident that pi is equal to H1, H2 is equal to H2, H1. It is also evident that no point not a vertex of the invariant triangle can be fixed unless pi reduces to a homology or to the identity. Such a transformation pi, when it is not a homology, is said to be of type 1, and is denoted by diagram 1, figure 48. Exercises. Prove that two homologies with the same center and axis are commutative, and hence that two projectivities of type 1 with the same invariant figure are commutative. Consider the figure of two points O1, O2, and two lines O1, O2, such that O1 and O2 are on O1, and O1 and O2 are on O1. A collineation pi, which is the product of a homology H, leaving O2 and O2 invariant, and an elation E, leaving O1 and O1 invariant, evidently leaves this figure invariant and also leaves invariant no other point or line. If A and B are 2 points not on the lines of the invariant figure, and we require that pi of A is equal to B, this fixes the transformation with two distinct double lines among the lines at O1, and the parabolic transformation among the lines at O2, and thus determines pi completely. Clearly, if pi is not to reduce to a homology or an elation, the line AB must not pass through O1 or O2. Such a transformation, pi, when it does not reduce to a homology or an elation or the identity, is said to be of type 2 and is denoted by diagram 2, figure 48. Exercise. Two projective collineations of type 2 having the same invariant figure are commutative. Definition. The figure of a point O and a line O on O is called a lineal element, OO. A collineation having a lineal element as invariant figure must effect a parabolic transformation both on the points of the line and on the lines through the point. Suppose AA and BB are any two lineal elements whose points are not on O or collinear with O, and those lines are not on O or concurrent with O. Let E1 be an elation with center O and axis OA, which transforms the point OA to the point OB. Let E2 be an elation of center AB O and axis O, which transforms A to B. Then pi, equal to E2 E1, has evidently no other invariant elements than O and O, and transforms AA to BB. Suppose that another projectivity, pi prime, would transfer AA to BB with OO as only invariant elements. The transformation pi prime would evidently have the same effect on the lines of O and the points of O as pi. Hence, pi prime pi inverse would be the identity or annihilation. But as pi prime pi inverse of b is equal to b, it would be the identity. Hence, pi is the only projectivity which transforms AA to BB with OO as only invariant. A transformation having as invariant figure a lineal element and no other invariant point or line is said to be of type 3 and is denoted by diagram 3, figure 48. A homology is said to be of type 4 and is denoted by diagram 4. Annihilation is said to be of type 5 and is denoted by diagram 5. It will be shown later that any collineation can be regarded as belonging to one of these 5 types. The results so far obtained may be summarized as follows. Theorem 29. A projective collineation with given invariant figure f, if of type 1 or 2, will transform any point P not on a line of f into any other such point not on a line joining P to a point of f. If of type 3, will transform any lineal element PP such that P is not on a point or P on a line of f into any other such element QQ. If of type 4 or 5, will transform any point P into any other point on the line joining P to the center of the collineation. The role of assumption P is well illustrated by this theorem. In case of each of these 3 types, the existence of the required collineation was proved by means of assumptions A and E, together with the existence of a sufficient number of points to effect the construction. But its uniqueness was established only by means of assumption P. In case of types 4 and 5, both existence and uniqueness follow from assumptions A and E. Exercises. 1. State the dual of Theorem 29. 2. If the number of points on a line is P plus 1, the number of collineations with a given invariant figure is as follows. Type 1, P minus 2 times P minus 3. Type 2, P minus 2 times P minus 1. Type 3, P times P minus 1 squared. Type 4, P minus 2. Type 5, P minus 1. In accordance with the results of this exercise, when the number of points on a line is infinite, it is said that there are infinity squared transformations of type 1 or type 2, infinity cubed of type 3, and infinity of types 4 and 5.
Projective Geometry, Volume 1. This book was written by Oswald Veblen and John Wesley Young. It was published by Blaisdell Publishing Company, London, 1910, and is now in the public domain. It is read by Jim Renholt, with programming and illustration by Jim Renholt, 2019. Thank you for listening.